All right, Math 201 students, this is a video over section 3.3 to 3.7. There were just a few examples that we did not have time to do while we were in class, so I'm wanting to go back and make sure we cover those. The first one was in section 3.3. This was find all the relative extrema of the particular function listed here. And so remember, relative extrema are found by taking the first derivative. And if we want, we could use the second derivative test with those critical values to then see if it is a relative max or min, but we could just do it using our increasing decreasing test as well. So if we take the first derivative of this function, it would be 3 times 2, so that's 6x squared minus 6. Set that equal to 0, pull out a 6. This then factors into x plus 1 and x minus 1. So we think that negative 1 and 1 could possibly be the critical values that would give us either a relative max or min. So then we're going to make our sign chart. And we're going to pick numbers on each side of those. Plug those into the first derivative, which is right here. So that would be negative 2 would give me a positive time, because 6 is positive, times a negative, times another negative. So that would be 2 negatives. That makes an overall positive, which means this region is increasing. If we plug in 0, we have a positive times a negative, which is a negative, which makes this region decreasing. And if we plug in 2, we get a positive times a positive times a positive, which means that overall region is positive, which means we are increasing. Now, to consider whether these are relative max or mins, we have to look at the pattern. So we're increasing, then decreasing. That means that there's a max at negative 1, and decreasing to increasing means that there is a min at positive 1. So we know we have a relative max at negative 1 comma something, and we know we have a relative min at 1 comma something. To find our actual values, remember, you plug them back into the original function. That's how we get our y values. So go back through. This would be a negative 1 times 2, so that's negative 2 plus 6 plus 1. That is going to be 5. If we plug in positive 1, we're going to get 2 minus 6 plus 1. So that's going to be a negative 3. So there are our ordered pairs for our relative max and relative min. Now the rest of those we did in class, so we're moving on to the next page. We did this kind of multiple choice question at the top, and then we did one of these graphing problems, so I've got the highlighted one that we did not do. This is sketching the graph of f only using the characteristics that you've been listed here. So anytime you have just an f of a number, this is going, and it's equal to something that's going to be an ordered pair. That was the ordered pair. I plugged in 3 for x and got 0 for y. If you don't know something about the first derivative, you know if your function is increasing or decreasing. So since this is positive for all x's, that means we are increasing on negative infinity to infinity. Now we know that the function, if you get the second derivative, that tells us about concave up or concave down. So this says from negative infinity up to 3, because its x is less than 3, this is a second derivative that's negative. So that means we're concave down. And from 3 to infinity, we are concaved up because our second derivative is positive. And that's all we know. So let's just sketch the one ordered pair we were given, which is an x-intercept. And then I know from that point on, I'm concaved up, which means I have to be going this way. And then concave down on this direction. And that does make sense because I'm increasing from left to right. So it looks like it's the function x cubed that's been shifted to the right 3. So that one's not too bad. This backside, this is the last part of section 3.3. We don't have any of these on the exam, but it's good to have a practice with if someone gives you the graph of f of x, not the equation. So I can't take the derivative of it physically using the equation. Is it possible to graph a rough sketch of the derivative? So let's talk about some key points on the original function and how they tell us how to graph the derivative, essentially. So this says that anytime we have a max or min, which means we have a slope of a tangent line that is 0. So notice that's happening at -1 and at +1. So because the first derivative is a graph where ordered pairs are an x comma slope of the tangent. So when we graph them, we're graphing the x value that's coordinated to the original function and the value of the slope of the tangent. So for example, the slope of the tangent here is 0. So when we graph these on the derivative, they graph as -1 comma 0 and 1 comma 0. So we can go ahead and put those 2 points here. Those are going to be x-intercepts. So places where you have a relative max or min are going to be x-intercepts on your derivative function when you graph it. Now, we also want to look at when do we have changes in our slope, in other words, increasing or decreasing. Notice that we were decreasing from -infinity to -1. We are increasing from -1 to 1, and then we're decreasing again from 1 to infinity. So that's going to be important because that has to do with our slope. If you're decreasing, you have a negative slope. If you're increasing, you're going to have a positive slope. And if you're decreasing, you're going to have a negative slope. Now, how does that translate to graphing the function? A negative slope means your y values are going to be negative, which means your function is going to be under the x-axis. And if you have a positive slope, your y value is going to be positive. So you're going to be above the x-axis. You're going to be graphing points where your y's are positive. It's good to find your point of inflection because that's kind of your steepest point. It's where the slope's usually the steepest, right where you change from concave up to concave down. If you could kind of imagine drawing the slope line here, which I've already written a lot, and you could count that, you know exactly what's the highest to graph your function, because this is the point where we kind of tip between the steepest slope. So I did this on my own paper. I drew a tangent line with a ruler, and I found that the slope, and this is at 0, my slope at x equals 0 was about 3/4. So that means that at 0, we would have 0 is a x point, and the slope of that tangent line there was 3/4. So we could graph that kind of about right here. Okay, so what I know now that I've kind of got my highest point in between here is that because this is decreasing, this all has to be y values that are negative. And over here was decreasing, so all my y values or slopes to my tangents are negative. And then in here, even though this goes up and then comes back down, these are all still slopes that are positive because we're graphing our y values as positive values. What's happening is this is saying my slopes were getting steeper and steeper because they're rising up to a higher y value, and then they go back down and kind of level back off at that maximum. So that's just a rough sketch of what that looks like. So let's do another one. Just again, rough sketch, not perfect. We're not looking for perfect. We're just looking for kind of details. So I'm going to try to thin out the ink on this pen so I can draw a little bit better. So this one's a little hard because the x's I have to approximate essentially here. I don't really know. Let's see, this point looks like it's at, let's see, this is -1 1/5, 1 2/5, -1 2/5, -1 3/5. So at -1 3/5, that's this point right here, that's where we have a horizontal tangent. This point right here looks like maybe it's happening exactly at -0.5. That we have a slope of 0 again at our tangent line. And then this one, I'm just rough estimating slope of my tangent, possibly, I don't know, somewhere between 1 1/5 and 1 2/5. So 1 point, we'll just say this is maybe 1.3. Rough estimating, okay? So, and again, that's all we want is a rough sketch. So we need to put those as our x-intercepts because remember, they stand for places where our slope is 0. So our y-intercept on our derivative function would be 0, because all of the y points on our derivative are always representing the slopes of the tangents at those specific points. So we know that at negative 1.35, which is about right here, we are going to have an x-intercept. And at about negative 0.5, we're going to have an x-intercept. And at about 1.3, which I'm guessing is about right here. Okay, so then this was decreasing down to that, then increasing, then decreasing again, and increasing. So what that tells me is that I'm going to be below x-axis, above x-axis, and then below, because I'm decreasing again, and then above. Okay, now if I want to get a little bit more detail, I need to find those points of inflection, kind of estimate. I think at -1, it's hard to tell because it's, it's a sketch. If I draw that tangent line there and count, I estimated it to be up 2/3. So we're going to say 2/3 approximately there. So that means that's the highest my graph's going to get because that's that point of inflection. So this is going to be -1 up 2/3, which I'm going to estimate to be about right around there somewhere. And then this also has a point of inflection going down because notice the bowl changes. This was concave up, concave down, and then at somewhere we flipped to concave up again. And it looks like it's happening to me just right around, let's see, maybe here. You kind of have to look for where you think the bowl's flipping. And so I would rough estimate this slope by drawing a tangent line. And that looks like, and that's a horrible tangent line. The one on my paper is much better. I had down 3/1, so -3. So that means the lowest that I'm going to get is down at -3, which is going to be below my graph. So 1, 2, 3, 4, 5. So there's -3. So right about here. So all I have to do in between here is draw what's going on and try to do the best sketch that you can. Of course, it's hard to do with this ink. So below the x-axis, because we were decreasing in the original function, above the x-axis because I had positive slopes, below the x-axis because I have negative slopes again, above the x-axis because I have positive slopes. So again, not on your test, but it's a good skill and it helps you to visualize what's really going on when you're talking about the derivative. So when we get into the next section, there were a couple of the word problems we skipped over. I'm going to go through those. And then we have, so this is sections 3, 4, 3, 5. They're kind of combined. We're looking for example number 4. It says find the production level that minimizes the average cost per unit. So we need to know our average cost function and we're going to try to minimize it, which means we're going to take a derivative. And instead of giving us that function, they gave us the cost function. But we learned in class that you can find the average cost function by taking this and dividing it all by x. So remember, c bar is c divided by x, number of units. So this would be x squared minus 8x plus 24. And then to minimize that, we would need to take the derivative. So c bar prime is 2x minus 8. So that means x equals 4 if we set that equal and solve it. And we could double check that that really does minimize by doing a test of our signs. And we would plug it into our derivative. So this says that that's 6 minus 8, so that's negative, and 10 minus 8 is positive. Therefore, notice that is a minimum because it is decreasing to increasing. So we would say, and they only asked us for the production level, which is the number of units. So 4 units is what they would need to produce to minimize the average cost per unit of the cost function. Now it says for this production level, show that the marginal cost and the average cost are equal to each other. So what you have to remember is that marginal cost is the derivative of the original cost function. This would be c prime. So I need to find c prime. So c prime is going to be 3x squared minus 16x plus 24. And then we would put in that production level we said that worked, which would be 3 times 4 squared minus 16 times 4 plus 24. So this is 16 times 3, so that's 48 minus 64 plus 24. I am getting a total of 8. okay? And that would be, remember, our marginal cost. So that would be in dollars. So let's talk about, does this match the average cost? Notice this doesn't say the derivative of the average cost or minimizing the average cost. It's the average cost function. So that was our average cost function, C bar, which was x squared minus 8x plus 24. If we plug in our production level that we think minimizes the cost, we can see that this does come out to the same. This is 16 minus 32 plus 24, which does equal 8. And then this last part says, sketch a graph of the average cost function to verify our results. Okay, so our average cost function, let's write it down again. It's that parabola we got when we divided the whole cost function by x. That was x squared minus 8x plus 24. So remember, if you plug in 0 for all of your x's, that will give you your y-intercept. So that gives me 24. So I need to know I need to start at 24 for my first point. So this is, let's count by 4. So 4, 8, 12, 16, 20, 24. So there's that point. We also would want to probably count by, ones down here. So 1, 2, 3, 4, 5, 6, 7, 8. If we plug 4 into this function, we already know what that is. That comes out as 8, because that's what we just did in this problem right before it. So 4, 8. So let's plug in something equally spaced on the other side and make sure that this actually is the minimum point here. We know this is a parabola. So if we do 8 squared minus 8 times 8 plus 24, because that is symmetric to this, it's 4 away from that. If that ends up also being 24, we know that the symmetry matches, and that actually would be the lowest point. So this is 64 minus 64 plus 24. So that means that 824 is a point. So notice we have that is our average cost function. Okay, so let's look on to number 6. We skipped over that one in class. This one is not hard. It just has a weird P function for the demand. So it says find the price that will maximize profits. So we're trying to get a profit function. That's the goal. And we're going to maximize it, which means we're going to take the derivative because we want to obviously figure out how to work our business. So it says find the price that will maximize profits for the demand and cost functions P equals 40 divided by square root of x and C equals 2x plus 50, where P is the price per units in dollars, and x is the number of units, and C is the cost in dollars. And then after we find that, we'll say when the profit is maximized, what is the average cost? So this is the first question. Find the price that will maximize the profit. This is the second question. So the first thing is you don't have a profit function unless you have revenue minus cost. Well, we don't have revenue yet, but we know that revenue is x times P. So if we do x times, and I would just move that up and make it x to the negative 1/2, because then we can multiply the x together and add their exponents. So this is like a 2 over 2 because it's a 1. So this has ended up being just 40x to the 1/2. So, or 40 square root of x. That's what you get for the revenue function. So that means my profit function is going to be revenue, which is 40 on the square root of x, minus my cost. So I need to minus both of those parts, so distribute that negative. So there's my profit function. Now I'm going to take the derivative of that so that I can maximize profit. So this is going to be, and if you want to write that as 40x to the 1/2, that's helpful sometimes. This would be 1/2 of 40, which is 20, x to the negative 1/2 minus 2. We're going to set that equal to 0. I like to move my square root of x back to the bottom. I'll add my 2 over. And this is where I like to cross multiply, so I'll put this over 1. So this becomes 2 square root of x equals 20. Divide both sides by 2. We get square root of x equals 10. To get rid of the square root, we square both sides. So it looks like the production level is 100 units, because that's what x stands for, but that's not specifically what they asked us for. I am going to check to make sure this maximizes profit first, because sometimes people blindly believe that and they need to check it. If we put in a 10 and maybe a 200 into our derivative here, square root of 10, well, let's do a nicer number. Let's do 9 or 4 even. 4 would be really easy. And I'm doing that because of the square root. So 20 divided by square root of 4 would be 20 divided by 2, so that's 10. 10 minus 2 is a positive. And let's do 144, something easy. So 20 divided by square root of 144, that'd be square root of 12. So 20 divided by 12 is going to be obviously less than 2. We'll show you. It is 1.66. If you do minus 2 from that, you end up negative. So notice that is a max. It is good to check that just so you verify that. But that is not what they asked for. This is the unit number of production level. They asked us for the price. So we have to go back to P equals 40 divided by the square root of 100. That's our price function. So that is 40 divided by 10. So they should be pricing at $4 per unit to get the maximized profit. Now, part 2, so this is all part 1. Part 2 says when the profit is maximized, that means you're at your max units that we just found, which was 100 units. What is the average cost? So you need your average cost function. So take C and divide everything by X. That would be 2 plus 50 over X. Because 2X divided by X is 2. 50 divided by X is 50 over X. Now we're going to evaluate that at the number of units, not the price. We want to know what would be the average cost per unit. So this is 2 plus 50 divided by 100. 2 plus a half, or $2.50 per unit would be the average cost. Okay, so that finishes up the word problem section because we did the other remaining ones in class. And all I had left, because we did say we were going to completely scratch number 4. It's not in WebAssign or on the exam. It's so it's not worth spending the time on that radical function in a summer session. So we're going to look at this other polynomial that I did not graph in class. So it says for the function y equals x to the third plus 3x squared minus 9x plus 5, which they so kindly factored for us so that we could easily find our x-intercepts. It says, what are your x-intercepts or y-intercepts, any intercepts essentially, your relative extrema, points of inflection, and asymptotes, and then use these to sketch our graph. So the first thing I'm going to note is that this is a polynomial, and polynomials do not have asymptotes, so we can go ahead and write none on that. And this would be really difficult to try to find the x-intercepts if they hadn't already factored it for us. So since they're already factored, we know what makes each of these factors equal 0. So negative 5 comma 0 is one of my x-intercepts, and 1 comma 0 is the other. To get your y-intercept, you probably want to plug 0 into the original equation, which would be 0 cubed plus 3 times 0 squared minus 9 times 0 plus 5. That is just going to be a 5, so that is 0, 5. So I found the x-intercepts by setting the factored form equal to 0, and I found the y-intercepts by plugging 0 into the function. So I'll write it down here so you know how we got each of those pieces. Okay, now when we start talking about max and mins, we need a derivative. So we need to take y prime. So this would be 3x squared plus 6x minus 9. We can factor out a 3. And then this factors nicely into x plus 3 and x minus 1. So that means my possible critical values are negative 3 and positive 1. We don't know if they are max or mins yet until we do our test. So we put our numbers in our chart. We pick, that doesn't look like a number 1. There we go. We pick values in each region, plug them into y prime, and I just use the factored form. So I have a positive 3 in front of everything. So I'm just going to put plus all the way across. If I plug in negative 4, I get a negative times another negative. So that's going to be a positive overall. This region is increasing. If I plug in 0, I'm going to get a positive and another negative, and that would be a negative overall. So this region is decreasing. If I plug in 2, everything comes out positive. So this region is increasing. So increasing to decreasing, decreasing to increasing. That means that my max is at the negative 3 and my min is at the 1. I need those as ordered pairs, so I have to go back to the original function and plug those in. I do at least know which one is which, so I can go ahead and put that I have negative 3 comma something and 1 comma something for my minimum. but we want those actual ordered pairs. And you can plug it into the factored form if you want. That might be quicker. So y equals -3 plus 5 and -3 minus 1 squared. That was the factored form. That is 2. That is -4 squared. That is 16 times 2. That is 32. So that is the y value for that guy. Then we would put in 1. And notice that's 6, but that's 0 squared, so that's 0, so that's going to be 0. And that should have been obvious since that was already a point we had up here, but it doesn't hurt to show the work. To get the points of inflection, you have to take y double prime. So this would be 6x plus 6, pull out a 6, and we get x plus 1. That means x equals -1 as a possible point of inflection. Put something on each side. Plug it into y double prime, that would be a negative overall, so that's going to be decreasing. And if I plug 0 in, that would be a positive overall, so that's going to be not increasing and decreasing. Sorry. We're on the second derivative, concave up and concave down. Get to talking too fast. So this is concave down. This is concave up. And because it does flip, that is a point of inflection. So that means at -1, we need to find the other part here. So go back to your original function. -1 plus 5, -1 minus 1 squared. That is 4 times -2 squared. That is 4 times 4, or 16. Okay, so once we have all of our points, we're going to graph what we know about the function and also use what we know about our behavior charts to help us fill in the shape. Now, I didn't write all of my increasing, decreasing intervals down, but we could. But remember, it is all listed above us, so we can always reference if we need to. What I do like to look at before I graph is that what's the highest and lowest y value and x values that I have to deal with. My x values are all pretty small, but my y values have to get up to 32. So I might actually want to move this part down, this line right here. Because I don't go very negative overall, but I do go up to positive 32. So let's redo that. A lot lower. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. I would like those to be more evenly spaced, but this is a rough sketch. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so it looks like we have to cross at -5. So that's one of our x-intercepts. And at +1. And we have a y-intercept at +5. So 5. We have a relative maximum at -3, 32. So go to -3, go all the way up to my highest point. I like to write that this is a max, so I know not to go above that when I'm graphing. And then down at -1, or at -1, which is right here, sorry. At -1, we have a point of inflection, which is at 16. So this was 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that is a point of inflection. That is where my bowl will flip. And then this is my minimum at 1, so it's good to mark that. And that is all of the points that I have. So what I know is that my function is increasing all the way up to our value of -3. That was what our chart had. So -3 was my max up here. So my graph is increasing, increasing, and I also know it's concave down at this part. So notice my bowl is going to be kind of flipped upside down. And that flip does not change until we get to the point of inflection. So now we're going to have the bowl flip concave up. And then we go down, and that's horrible. Sorry. Try my best to draw with this pen. And we have a minimum. So notice we're increasing, decreasing, increasing, just like we had outlined here, concave down and concave up. And that is it. All right, so hopefully you guys enjoyed this video and that clears up any other problems that you might see in your homework as well. And I will see you guys on Tuesday after our 4th of July holiday. So study hard for your tests. Make sure you bring all your questions from either the instructor choice packet or the review that day on Tuesday. You can also find me in my office 2 hours before class if you have lots of questions. Have a good weekend.